Okay, so what we've done so far here for week 12, and we didn't have class because it was election day on Tuesday, but what I did just cover were further instructions on how to dial in that summary 3, and what I'm going to do now is cover problem set 2, and then we'll cover chapter 11 in the third half hour. So let's go and look at problem set 2. Go for it, yeah.
So when you said parabolic, is that the same as quadratic?
Parabolic and quadratic are the same.
So
Yeah. When things are around long enough, we just invent new names for it. You could also call it a second order equation. Yeah. Birthday problem. Gone through the practice problems. Lecture 3, cold problem warm-up. Look at all the problems on this. Why don't we just keep creating problems? Let's just find problem set 2. Okay, assignment 1, problem set 2.
You search the word problem.
I am just searching it.
That's sweet.
Problem set 2. There it is. Let's take a look at that. Are we, no, I'm a little confused. Is it week 10, or is it week 11, or week 12?
Week 12.
It's week 12, yeah.
But I think it is week 11, though, because we're on chapter 11.
I have a hard time doing that.
You know, if we're on time or if we're ahead, doesn't matter. It's all, yeah. We're either on time or ahead. It's fine. All right, all 5 problems are similar to those covered in the text or class. Remember to show all calculations, terms, and units and organize well. Unless otherwise specified, give answers to 3 significant digits. We covered that before. No need to submit as PDF. You can, if you want. You can submit as Excel or as Word or scanned. You know, so I'm making it easy on you in terms of how you submit this thing. Refer to coal reserves and production data given in table 5.1 of your text. At current coal usage and production ratios, the USA has how many years left to extinction? If the USA were at China's current, how many were left? And if the USA were given, how many years are left? Okay. Now, this is fairly simple. It's just algebra. Nothing too crazy here. So let me just give you an example. I'm not going to use the numbers. But let's just say we've got the U.S. here, and we've got China here, and we're going to have reserves, and we're going to have production. And over here we're going to have reserves, and we're going to have production. And in your book, there will be numbers, and
Do you want to get the up-to-date numbers? Is that possible? Isn't this from 2012?
I want to use, you could make it harder for yourself,
Right.
or you could use what's in the book.
Okay.
Okay.
Well, yeah.
If you, the issue is if you attempt to make it harder for yourself, it's going to be, there's 2 issues. There's 2 issues. One is, are you able to do the modeling? And that's really the crux of the course. Can you do the modeling is one thing. Can you do the research is another one. Energy 101 is not as focused on the research as 102 is. When we get to 102, I'm going to say, yeah, go out, dig into the literature, find the up-to-date values, etc. 101 is more like, can I do the modeling? And the research is in front of you. The numbers are in the book. And the nice thing about using the numbers in the book, is that when you go to compare your answers to everyone else in the forum, you won't be as confused. Okay, so here's how I would attack this algebraically. I would just call this number reserves US, and I would call this production US, and I would call this reserves China, and I would call this production China. And the way to think about this, it's a lot like the energy and power problems that we've done in the past. So it's kind of nice to have a figure. So here's the U.S., here's China. Now, the entire chunk here is, you can just think of as the coal reserves. And if we're, let's just say, shaving this much, so there's the reserves of the U.S. And this is the production of the U.S. And this chunk right here are the reserves of China. And here is the production of China. Okay. And then what we can do is draw another graph.
Would you like us to include a graph?
Nah.
Okay.
I mean, if you want, it's easier for me just to look at it this way. So we can just call this year 0. You can also call it year, whatever's in the book, 2013. I don't know what number's in the book, but there it is. And right now, this is our reserve, U.S. And then each year, as this number goes down, this little chunk right here is the production. That's what's being dug out of the ground. And then at some point, you get to year N in the future. So again, with problem set 2, we're trying to predict the future. And then you do the same thing. Here's the reserves of China. Here it is now, year 0. You know, each year, kind of looks like a Dr. Seuss staircase there, doesn't it? Production U.S. And here's a, you gotta wonder, man, what was that guy doing?
Yeah, where you trip on the top stair.
Building standard.
Trip going down and trip going up.
I don't know if I told you guys, I just got invited to go to, and I can't remember, it's either Bellevue, no, it's not Belgrade. It's either Bellevue, Washington, or Bellingham, Washington. They're gonna film me in 3D giving 40 10-minute lectures on engineering
Jeez.
in January. It's gonna be a trip.
Wow.
And so, but the hardest part is it's just me and the camera. I don't have like props or anything, so.
Or any,
Wow.
are you gonna be?
Yeah, but I'd bring my own props.
I'm gonna bring my own
Are you gonna be
props.
speaking in front of people, or?
It'll just be a studio
Oh, okay.
In
So it's
3D?
gonna
in
be-
3D. It'll be, you
Can be
know,
filmed from all angles.
well, you know how when they filmed, it'll either be that or just stereoscopic. As I'm thinking, like,
Yeah.
do I really need to, make sure my shirt's tucked into the back? I don't know.
Well, at least you'll have time to prepare and then also have cuts and then continue.
So 40 10-minute lectures?
Yeah,
That's
yeah.
really good.
It's gonna
You
rock.
can just get on a roll and keep going.
I will, yeah, over 5 days, so 8 lectures a day. Anyway, so what we're trying to do here, no, it's gonna be fun. So what we're trying to do here is predict, so this is gonna be N US and N China. So the equation, let's see if we can do this. N US, so this is the number of years left, equals, well, it should just equal the reserves, US, over the production in the US, right? Because the more you have, the longer it's going to last, and the quicker you dig it out of the ground, the shorter it's going to last. Pretty simple. N China, this number right down here, the number of years left, equals the reserves in China over the production in China. And that's it. Pretty simple.
Just plug numbers in.
That's it. You plug the numbers in and you go. And now we have a model. Now, the other two things that are asked for, were asked for N U.S., China, which is basically the number of years left of U.S. coal if we produced at China's rate. So it's going to be reserve U.S. over production China. The other one is going to be N China, comma, U.S., just flip it around, equals the reserves in China over the production at the U.S. rate. It's just assuming like we exported all of our coal to China and they exported all of their coal to us. That's kind of all it comes. Oh, hey, here, take it. Yeah, so that's problem one.
Do you know about the quality of each type of coal?
It's all over the map. You know, it is all, literally all over the map.
They probably have quite a bit more though.
I can't remember off the top of my head. Australia's got a big issue with it too.
I can just envision the map I saw in the book of the coal reserves.
Yeah.
Was that
Beg your pardon?
calculation that you did, but just the reverse of the first? So like the year,
Yeah, every one of these is the same. So again, just kind of look at this entire chunk. This entire chunk, RUS, is how much coal there is under, you know, U.S. soil. And here's our production, same thing in China. I drew China's smaller, but it could be bigger, and I don't want to sway your opinion one way or the other. I'm just showing the modeling. And so again, the bigger these stair steps are, the shorter it is to the end of coal. Same thing over here. Bigger the stair steps, the shorter it is to the end of coal in China. England put their last lump in a museum, as I want you to know.
good for that.
Well, they didn't have any left. They didn't have any choice. I think they said they've got, you know, they probably had like a year or two left underground, but it's just, it was not economically, you know, you just gotta just keep digging deeper, and, you know, and you got miners trapped in the whole mess, so, yeah,
There's
don't
also
bother.
a way to just say we want natural gas.
Well, maybe. I think really what we're seeing here is the economics of renewables are going to drive it, not just
Yeah.
some policy or whatever. It's
Somebody
just,
needs to be the
It
pioneer.
makes more sense,
yeah,
you know?
yeah. Okay, so again, to answer your question, all we've done here is just flip those two numbers. We pretended that we were digging through that U.S. reserve at Chinese rates. Here we were digging through the Chinese reserve at U.S. rates. All right. So the next question. This is a good one. I love this one. 900 degrees Fahrenheit, and we're coming back at 100 degrees Fahrenheit. What's the theoretical Carnot efficiency? You can remember back to chapter 4, we did Carnot. So eta equals T hot minus T cold over T hot. Now, the issue, so Kelvin is to Celsius as Rankine is to Fahrenheit. And this, I mean, Google's right there, right out in front of it. Say, hey, we've got our own conversion. Pretty simple math. Let's just do Fahrenheit. It also allows me to be a terrible speller. But so 32 degrees Fahrenheit. So freezing at water freezes at 32. That's the temperature at Rankine. And so we can pop in the numbers. 100 degrees. So the point is that when I run these numbers, these have to be absolute temperatures. And let's just see, there's got to be some cool, yeah. There it is. There's your scales, all four of them, right next to each other. So we cannot run this math in Fahrenheit or in Celsius because they're both based on the freezing and boiling temperatures of water. Rankine and Kelvin are based on the freezing temperatures of the universe. And that's what the Carnot efficiency is based on. So it's absolute temperature. So what you want to do, you can convert Fahrenheit to Kelvin if you wanted. You could also just convert it straight into Rankine. And if you want to do both, all the better. Then you can convince yourself that Carnot efficiency calculated on the Rankine scale or the Kelvin scale are equivalent. Okay, so that's your Kelvin or Carnot efficiency. Some pals of mine constructed a hot tub to use at our campsite utilizing our campfire. We wanted to determine the energy, so we referred to box 5.6 for help. Hot tub had 500 gallons of water. Temperature was at 45. On its first use, we lost track of the campfire and it started to boil. How much energy did we expend to get the water to boiling? So they had 500 gallons. Here's your equation for that. 500 gallons. And T1 equaled 45 degrees Fahrenheit. T2 equals 212. So the equation we're going to use here is energy. So I think that's what the question asked for. How much energy? Energy equals C sub P. Now, in this case, the trick, and I'm not going to give the answer away. C sub P times M times delta T. That's the equation you're going to use. Because you want to know what this is. So you will be able to find the specific heat capacity for water. I've given you 500 gallons, so you'll be able to find that. You'll know that. You know the mass, and you know the change in temperature. So this is one equation and one unknowns. You know the specific heat capacity of water, you know how much water is there, and you know the change in the temperature. That will give you the energy. That's all you need to know. And the thing to keep in mind are just the units. So we've given this to you in Fahrenheit. We've given you the volume of water. You may or may not need to convert the volume to mass because typically the heat capacity is given in joule. And so there are many different ways to do C sub P. So C sub P could be given in, well, the units are energy per kilogram per Kelvin, or energy, well, let me do it this way, sorry. Let's do it this way. Energy per mass per temperature. So that can then become joules per kilogram per Kelvin, or joules per kilogram per degree Celsius. It's the same thing. You could also write it in calories per pound per degrees Fahrenheit. I mean, there are all kinds of ways to describe this, just as there are all kinds of ways to describe energy. You could do it in BTUs per gram per degrees Fahrenheit. There's a bunch of different ways to do it. So the challenge here is just to make sure you're using the right units. It's the same thing as like, oh no, officer, I wasn't speeding, I was just doing 45. Well, you were doing 45 meters per second, which is 90 miles per hour. Sorry, you were speeding. I was doing 45. 45 what? Okay. Bonus question. We got distracted long enough that 5 gallons of the water boiled away. If we were able to collect the steam that boiled, how much energy would we return from the steam? So, let's just grab that guy. I think this is in the book as well. Fluids. So this is just going to tell you, again, you can measure it in kilojoules per kilogram, BTUs per pound. This is just telling you how much energy it takes to go from liquid into vapor. Because it takes energy to do that. So what he said for the bonus, we were sitting here, and we know that T2 equals 212. Now we've got the thing boiling away, and we were at 500 gallons. We know when we got to T3 still equals 212. The water cannot get hotter than boiling because we're at atmospheric pressure. That's just what happens. And if you're at elevation, that number goes down a little bit. But now we're at 495 gallons of water, and we've got 5 gallons. You can convert that to mass, because obviously there aren't 5 gallons of steam sitting up where there's probably, a few hundred gallons of steam floating around, and then the clouds form, and it starts raining, and whatever. But, so convert that 5 gallons to mass, and back to this little table. You can convert it to pound, BTUs per pound. So just use your units conversion, and that's why we did that problem set 1, so you know how you're comfortable with units conversion, and that's how to run that bonus problem. Okay. We'll play around with that. We'll play around with these two next time. I want to get into chapter 11. Yeah, we'll play around with that. So work on that. We'll play around with 4 and 5 next Tuesday. So we'll take a break, and then we'll dive through chapter 11. I told you we did that back of the envelope where the equivalent coal combustion is the same as one coal car going 180 miles an hour?
Yeah.
Yeah, okay. It's that type of problem. All right, where am I here?
You looking at it?